I'll leave it to you. Okay, so we were discussing this heat conduction equation in Cartesian coordinates, right?
Yes, sir.
Yes or no?
Yes, sir.
So we said that the equation 9 is the most general form of the heat conduction equation in Cartesian coordinates, right? And from equation 9, how to introduce the assumptions like if the thermal conductivity is constant, how the equation will look like, or if you say that consider the steady state condition, then this term will go out, and how the equation gets reduced to this form, right? And at last we wrote the expression for the one-dimensional heat conduction under steady state without internal heat generation or with no energy generation term. Means the Q dot term is not there in the last expression. And I said this is the most simplest form of the heat conduction equation or heat diffusion equation in Cartesian coordinates, right? So remember at least equation 9 and based on the assumptions you can later on reduce it to the form of as that of equation 12, right? I asked you to derive the equation in case of cylindrical polar coordinates and spherical coordinates. I hope you must have done that. So I am skipping this part. You just note down this equation. Write down this final form of the equation, this expression, this one, because we need this equation while analyzing the cylindrical coordinate system problems. So write down this expression. So the heat conduction equation or heat diffusion equation in cylindrical coordinates is given as 1 upon r dou by dou r into bracket kr dou t by dou r plus all other remaining terms. So write down as it is. So the
Sir, can you show the previous slide of the cylindrical coordinate?
So cylindrical coordinates, you can note down this coordinate system, this one. So how the element is taken? So you have a cylinder, and this is the element cut from the cylinder, and this is exaggerated view of the element, right? And what are the dimensions of the element? They are dr along the radius. This dimension is dr. Then dz is the vertical dimension along z axis, this one, and this is theta, right? So this dimension is d theta, it is changing, right? D theta, and as this length changes with respect to the radius, you will find that length is given as r d phi. Notation is phi, excuse me, not theta. So make it phi. So this length will be r d phi, right? And rest of the terms are pretty similar to what we did in case of Cartesian coordinates. So we have the three heat transfer rate of heat transfer terms like QR, Q phi and Qz, which are entering the control volume, and the three remaining terms like Qz plus dz, Q phi plus d phi, Qr plus dr. So these three are the rate of heat transfer going out of the control volume, and then you can add the heat generation term, right? So E dot G you can add, or E dot ST you can add for that matter. So we know that Q dot is the volumetric heat generation rate. So you can incorporate this term, right? And after following the same procedure as that of the Cartesian coordinate systems, you will end up getting this equation. So in between steps, I left it for you to find out. So write down the final form now. So 1 upon r dou by dou r of kr dou t by dou r plus 1 upon r square dou by dou phi of k dou t by dou phi plus dou by dou z of k dou t by dou z plus q dot is equal to rho cp dou t by dou t. Is it all?
Yes, sir. Done.
Okay, fine. So should I go ahead now? So on
Yes,
next
sir.
slide you will find the element which is taken from the spherical coordinate system, and the same philosophy is applied there as well. The only thing is here the directions were r, phi and z. So there you will find the directions will be r, theta and phi. So we have a sphere like this, and this is how the spherical element is cut from the sphere, and the exaggerated view is shown. And similarly, we have the terms like QR, Q phi, Q theta, and the corresponding terms which are going out of the control volume, and then the dimensions of the element, like this is r d theta, the vertical this distance, which is curved actually. Then the dr along the radius, and this r sine theta d phi, this length. This is again the curved face, right? So again follow the same procedure as that of cylindrical or Cartesian coordinate system, and you will end up getting this form of the final equation. Write down this equation, the final form of the heat conduction equation or heat diffusion equation in spherical coordinates. So this is three-dimensional. Most of the time what we will do is when we study one-dimensional heat conduction, we will only take into account this term, and if there is heat generation we have to take into account this term as well, and if the process is unsteady we have to take this term, this one. So we will talk about only these three terms here most of the time. So in this equation, at least you should know this term, first term plus this q dot is always there, and the rho sec dot t by dot t is there in both equations, cylindrical as well as spherical coordinate system. However, I would suggest you better try to derive this equation. It will be helpful to you. Now, if you have noted down this equation, I will go ahead.
Yes, sir, we are done with it.
Okay, fine. Solve this one. The temperature distribution across a wall 1 meter thick at a certain instant of time is given as temperature is function of x. That's why this you should read it as temperature is function of x, not t multiplied by x. So this is a plus bx plus cx square, where t is the temperature in degrees Celsius, and this distance x is given in meters. While these coefficients or constants a, b and c, these coefficients are given. A is 900 degrees C, B is minus 300 degrees C per meter, and C is minus 50 degrees C per meter square, right? Then we have uniform heat generation, where the volumetric heat generation rate is given, Q dot, 1000 watt per meter cube, is present in the wall of area. The heat transfer area is given 10 meter square, and the properties of the wall material are given. Density is 1600 kg per meter cube, thermal conductivity is 40 watt per meter K, and the specific heat Cp is 4 kilojoule per kg K. Clear? Your job is to find out or determine the rate of heat transfer entering the wall. Entering the wall means at x equal to 0 if you are using the coordinate system the way we discussed previously, and leaving the wall at x equal to 1. Then second, you have to determine the rate of change of energy storage in the wall, means we are talking about this E dot St, this term. And the last one, determine the time rate of temperature change at x equal to 0, 0.2, 0.5 meter. Right? So time rate of temperature change means we are talking about change in temperature with respect to time. We are talking about this term, and you have to evaluate this at x equal to 0, then x equal to 0.25, and x equal to 0.5 distance. This is what they have asked. So have you understood what is this problem is all about? This one Cartesian coordinate system, and the problem is one-dimensional heat conduction with internal heat generation. I repeat, this is the problem for the one-dimensional heat conduction with internal heat generation, because this Q dot term is given, right? Hello, is it clear?
Yes, sir.
Okay, how to solve this? Now I am skipping some of the steps. So we know our 6-step approach we have been following throughout. So note down what is known to you, then find out I have already noted on this. So we have to find out what is Q in entering through this space, and what is Q out going through this space, right? Then you have to find out the rate of energy storage, E dot ST, this term. Now E dot G you can find out because Q dot is given. So this energy generation rate E dot G. So this is volumetric heat generation rate. Means Q dot is the heat generation per minute volume, right? So that's why the unit is watt per meter cube. So the E dot G term will be calculated as this volumetric heat generation rate Q dot multiplied by the volume of your element, right? So A is the area, which is this space area, and L is nothing but this thickness of the slab. So this A into L will give you volume, multiply this by this Q dot, that will give you the energy generation term, right? And then you have to find out dou T by dou X at X equal to 0, 0.2, 0.5. I already talked about this. The schematic representation is already shown here only to reduce the time which we are going to spend here. And then the assumptions, most of the things are already mentioned in the problem. The one-dimensional heat conduction, then the CP is given, CP, CV same for this type of material incompressible we have taken. Isotropic medium is given, means K is constant, right? And there is uniform internal heat generation. So this Q dot is uniformly distributed throughout this space. This is what the meaning of the last term, uniform internal heat generation. And to do the analysis, what we need is the help of the Fourier's law, and then the energy balance, right? Energy balance, and the last one is the heat conduction equation in Cartesian coordinates, right? And comment if you wish to comment after solving this problem, we are right? So how to solve? Answer is given on the screen. Yeah, you can try it and check whether your answer matches with whatever I have put on the screen. Fine. I will find out Q dot in first, or sorry, Q in first. This is the rate of heat transfer entering through this slab. So we will use the Fourier's law of heat conduction, right? So we will write Q in as minus Ka dt by dx. Now this is at Q in, this x is equal to 0 and here x is equal to L, right? So I will write this dt by dx means temperature gradient at this level, means at x equal to 0. So if I put the temperature gradient here, what I am trying to find out is Q in, right? So similarly, if I want to find out what is Q out, so I may write the equation like this, minus Ka dt by dx, and now this time I will write x equal to L. So evaluate this gradient at x equal to L, means at this phase. Clear? Is it clear? So it means, first of all, you must know what is the temperature gradient, right? And then you can find out this Q in and Q out. Now how to find out the temperature gradient? By dx, I will find out.
Differentiate.
So temperature T as a function of x, this equation is given a plus bx plus cx square, right? So if you take first derivative, you will write dt by dx is b plus 2cx, right? And if you write second derivative, you can write it like this, d square t by dx square is 2c, right? So we are talking about this term, the temperature gradient dt by dx. So this dt by dx at x equal to 0 will be equal to b. So whatever value of b is given, minus 300, or is it minus 300? Value of b is given here, minus 300, right? That minus 300 value. Then you can also find out what is dt by dx at x equal to L. So at x equal to L, it will be b plus 2c, and x will be replaced by L, right? Then put the values like minus 300 plus 2 into, what is the value of c? I think it is minus 50 into meter, and c is minus 50. So this will be 1, length is 1. So this will give you the temperature gradient at the left phase, this will give you temperature gradient at the right phase, and then simply find out what is this Q in, which is minus K. Now the K thermal conductivity is given
40.
40.
And area is 10.
40 into 10 multiplied by this minus 300. So this will give you Q in, right? And Q out will be minus 40 minus K A into dt by dx at x equal to L, means this value. So minus 300 plus 2 into minus 100, right? And write down whatever the values you get. So this answer will be, bolo.
Sir, 1,20,000 watt.
What? Sign is plus, right?
Yes, sir. Positive. Sir.
So it is 120 kilowatt, which matches with this value. Fine. Second is?
Sir, 1,60,000. Same answer. 160,000.
What? This is also matched.
Yes, sir. Yes,
Fine.
positive.
Now find out the energy storage, E dot ST term. So for that, what you need is energy balance, right? Energy balance is required. So you have the element, let us say like this. So Q in is coming, Q out is going, and there is this E dot G term, energy generation within this volume, right? And then you are trying to find out what is this E dot ST. So E dot ST, energy storage rate, will be determined using these things, right? Get me or not? So Q in is coming, plus there is this E dot G already present, and minus Q out is going. So that will give you the energy storage within the control volume, correct? So what is E dot G now? I already talked about this. The internal heat generation rate, this will be given as Q dot, that is volumetric heat generation rate, multiplied by volume. So find out that term, put it here. Q in is known to you. E dot G will calculate from here, and then solve it and find out what is this E dot S, right? So this is 1,20,000. Then the energy generation term, this will be 1,000 into 10 into 1. So 10,000, right? Minus this term, 1,60,000. This one. So we can find out the energy storage rate E dot ST is minus.
Yes, sir. Minus 30 kilowatt.
Minus 30,000 watt. We are solving in watt, that's why I am writing it in watt only, I'm not converting it. So it is matching with this value, correct?
Yes.
Minus. So what you understand from this minus sign? See, the energy storage within the control volume is decreasing. It means what? The more heat is transferred away from the more heat is transferred from the control volume to the surrounding, right? Compared to the heat transfer from outside to the control volume. Get me or not? Hello. So that is what that minus.
Yes, sir. Got that.
Okay. Now find out this. This is tricky part. Find out the temperature gradient dou T by dou T. Temperature variation with respect to time rate of change of temperature, dou T by dou T. Now for this, what you require is the heat diffusion equation. Now write down the form of the heat diffusion equation with constant K constant, and with internal heat generation term Q dot. And it should be the unsteady part, because we have to find out the variation with time, right? So the form of the equation will be dou square T by dou x square, right? Because K we have taken a constant, right? Plus, bolo. Is it Q dot upon K? This must be equal to 1 upon alpha dou T by dou T. Check. Is this equation correct?
Sir, in equation number 10, right, sir? You are telling me.
See, you have to reduce this equation. This equation we are reducing, right?
Yes,
So
sir.
as K is constant, you can refer to this equation now, right?
Yes, sir.
And it is one dimensional, so these two will be cancelled, right? So this term will remain because internal heat generation is there. So I am evaluating, I am actually simplifying this equation 10. So dou square T by dou x square plus Q dot by K plus 1 upon alpha dou T by dou T will give you equation. I have written here, right? So write dou square T by dou x square. Fine. Now you will be in position to find out this dou T by dou T provided you know these two terms. Now it is time to find out the second derivative of this temperature or second gradient. So we have already solved this d square T by or dou square T by dou T square. This is equal to 2C. Means this is independent of x. It does not depend on x. So whether you calculate this term at 0, 0.25 or 0.5 meter, it is independent, right?
But sir, what about alpha, sir? Alpha भी find करना है इनको ना.
So find out alpha. What is alpha? Thermal diffusivity. So what is the definition of alpha? It is K by rho Cp. Correct? Hear me or not? K by rho Cp. So this is known to you. K is given. Thermal conductivity is 40, right? Rho is 1600 and Cp is, now there is one problem here. See, this value is in watt per meter K. This is in kg per meter cube, so it will be in kg per meter cube. Density will be always given in kg per meter cube, right? Cp value, this is given in kilojoule per kg K, 4 kilojoule per kg K. However, I recommend you always use the value in joule per kg K. Otherwise, there will not be the consistency in the units. Huh? Otherwise, you should use this in kilowatt per meter K. But generally, we do not use kilowatt per meter K unit for the thermal conductivity. So, the good thing is use this Cp value in joule per kg K, even though it is given in kilojoule per kg K. Does it make sense?
Yes, sir.
So
Yes,
this
sir. Even
alpha
got the answer.
6.2 into 10 raised to power minus 6, right? Correct? So you can put it here, then Q dot is known, K is already known, and this we already calculated, which is 2C, right? So from that you can find out this dou T by dou T at 0.25 or 0.5, one and the same value you will get. And that answer will be, is already mentioned here, this value, minus 4.69 into 10 raised to minus 4. Does this value matches with your calculation or not?
Yes, sir. Yes, sir. It's exactly the same.
Okay. I think Abhishek Mishra told me right now. Abhishek, na?
Yes, sir.
Is there any other student in meeting who is doing this calculation? Any other student apart from Abhishek Mishra? Or is
Yes,
it
sir.
like I am teaching only Abhishek Mishra?
Hello,
Others
sir.
are also encouraged to participate in discussion. हाँ बोलो. Hello. Go ahead.
Yes, sir, do it.
So it's matching.
Yes, sir, it's matching.
Very good. So what you conclude from that minus sign, then I leave it to you. Why that minus sign is there in the this temperature?
Sir, it means temperature is decreasing with respect to time.
So it is decreasing as the time advances. Decreasing. This is what the significance of that minus sign. Fine. Now, shall I go ahead? So
Yes,
that's
sir.
all about introduction to conduction, the very basic things we have talked about. Now hereafter, the next topic of discussion will be the one-dimensional heat conduction. One-dimensional heat conduction. So we'll talk about the standard cases like plane wall, the hollow cylinder, hollow sphere, then the composite wall, composite cylinder, and composite sphere, something like that. Then the concept of thermal resistance, then contact resistance, and how to find out the thermal resistance, the definition of overall heat transfer coefficient, all that stuff we will see in the coming slides.
So, sir, do we have to only derive the equations, or we have to also solve numerical based on them?
Which equation you are talking about?
No, sir, you told me that sphere and all. So, do we have to also solve the numerical in that?
I am going to cover it in class, or if you want to do it on your own, I'll be happy. Okay, just let me take the different slides now. So one-dimensional steady-state conduction. Can you see my slides?
Yes, sir, visible.
Fine. Now, why to study one-dimensional heat conduction, or what is the idea behind studying this? So look at the first bullet. The temperature gradients exist along only a single coordinate direction. So we already talked about the example. So let us take an example of a slab like this. So temperature is varying along x direction alone. So this is typical case of one-dimensional problem, right? Is it clear? So the direction of the heat transfer is also along x direction. We have talked about this. Next point. The system is characterized by the steady state conditions. We know this means we are not going to take into account the variations in properties like temperature with respect to time. So this term we will neglect, or we will not take into account dou T by dou T, right? So we will say that the temperature is independent of time. We'll consider one-dimensional steady state conduction with no internal heat generation. Means this Q dot term will not be considered to begin with throughout this chapter. So Q dot term is not considered. We will consider it in later part of the content, but not right now. What is the objective out of this? So the objective is to determine the expressions for, now two things are important: temperature distribution, this word temperature distribution, and another is the rate of heat transfer or heat transfer rate. So the sole exercise is done to find out these two quantities, temperature distribution and the heat transfer rate. And if you know the temperature distribution, I explained this before also. So if you know somehow if you are in position to determine the temperature distribution within your domain, then with the help of the Fourier's law, you can find out the heat transfer rate. This we talked about previously, right? And we will do this exercise for the three standard cases: the plain wall or a slab, the hollow cylinder, and a hollow sphere. So you understood the objective? So in today's class, we will finish discussion on these three cases: plain wall, hollow cylinder, hollow sphere. So should I go ahead now? Remember, the two things are important here: the temperature distribution and the rate of heat transfer. Now look at the first case, the plain wall. So you should draw these diagrams quickly and write down whatever I am going to project it on the screen quickly. So I am starting with the standard form of the equation. This is again the most general form of the equation. The only thing is, instead of writing 1 by alpha here, that k is kept inside. So k is considered as a variable with respect to x, y, and z. So that's why you will not find that k term here, and rho Cp is kept as it is. So this is just one step before that equation 7 or 8, right? So that equation I am writing, and then the slab having the length L. So at this point x is equal to 0, right? And here x is equal to L, and x is measured in this direction. So Ts1 is the temperature of this surface, T1. S stands for surface, and Ts2 is the temperature of this surface at level 2, right? And just don't.
Sir.
Huh.
Sir, as it is a plane wall, so why the terms like rho by rho y and rho by rho z are present here?
Rho by?
I mean, sir, partial differentiation with y is
No,
given
no,
in the
we
equation.
are going to simplify this. See, this is our starting point. We are going to simplify this. I have not talked about the simplification yet. Get me or not? Hello?
Yes, sir. So, yes,
See,
sir.
I
Yes,
am
sir.
going to talk about all that. Temperature gradient, temperature variation is not there with respect to time, so this will be 0. Then this is one-dimensional problem, so these two will be 0. There is no intelligent generation, so this will be 0. So give me some time and then I will explain. Or otherwise, you want me to do it fast?
No, sir. It's fine.
Okay, I am asking all of you. Are you aware of all this? So if you are aware, I will skip this part and I will go ahead.
Yes, sir. थोड़ा सा part sir पहले किया है मतलब उसमें
Okay,
last time
fine.
diffusion.
With all these assumptions, the equation will be reduced to this form. Now I am integrating this equation twice, right? So I am skipping the steps in between now. I have not written what happens when you integrate this equation twice, right? So integrating twice, you will get the temperature distribution. So temperature as a function of x will be written as C1x plus C2. So as this is the second order differential, I have two constants of integration, constants C1 and C2, right? Correct? So should I go ahead? Now your job is
Yes,
to
sir.
find out these constants C1 and C2. So you need two boundary conditions to do this, right? So those two boundary conditions are here. So use these two boundary conditions. So first boundary condition is, call this as boundary condition 1. So the condition you should read it like this: at x is equal to 0 means this temperature T is equal to Ts1 means this temperature, and at x is equal, this is second boundary condition, at x equal to L, this temperature is given as Ts2 means this temperature. These two boundary conditions we will use, right? So if you use the first boundary condition here in this equation 2, this x will be 0, then C2 will be simply this T, and that T is nothing but Ts1. So this is how C2 will be equal to Ts1, or Ts1 will be equal to C2. So this equation you will get, right? So value of C2. Now if you use the second boundary condition here along with the value of C2, which is Ts1, put it here, then what you get?
So C1 equal to TS2 minus TS1 by L.
So you will
Yes, sir.
get the value of C1 like this. Correct? It's very simple mathematics, nothing big in this. You must have studied all this in mathematics, right? So you got the values of C1 and C2, then put it back to equation 2 and you will get this expression, right? Are you getting this
Yes, sir.
equation?
Got. Yes, sir. Yes, sir. We got.
Then you will write the expression for the rate of heat transfer Qx. So I am using the standard equation, Qx is minus K dt by dx, then minus Ka by L. I am just putting that dt by dx term here and rewriting the equation. So note down equation 7 now. So Qx will be Qx is equal to, now this minus sign is replaced because I am writing Ts1 minus Ts2 and not Ts2 minus Ts1. Huh? That's why that minus sign is replaced here. So actually we write the temperature gradient as the final minus initial, but here I am changing the sign itself. That's why minus sign is taken here. Clear? So once you know the rate of heat transfer Qx, then you can write down what is the heat flux. So Qx double dash is the rate of heat transfer per unit area. So Qx by A. So this equation will be simplified like this. So this A will go out. So K by L, Ts1 minus Ts2. Note down equation A. Clear? Hello.
Yes, sir. Clear.
Any other student apart from Abhishek Mishra? Any other
Yes,
student?
sir.
Yes. Okay. Or otherwise, if I am supposed to teach only Abhishek Mishra and if he has already gone through all this, it will take hardly 15 lectures for me to complete your syllabus. You want me to do that? Not more than that. 15 lectures are more than enough. Okay. So note down the last form of the expression, that the heat flux will be given by this expression or by this Qx is Ka by L, Ts1 minus Ts2. Fine. So this is about the plane wall. Now the concept of thermal resistance. So you must have studied in electricity. What is electrical resistance?
Sir, the positive flow of current. So similarly here maybe the positive flow of heat or temperature. Yeah.
The electrical resistance definition is it is the ratio of the driving potential to the quantity which is flowing. So in case of electricity, the flowing quantity is current, and the driving potential is your the potential difference, right? Delta E, potential difference. So the electrical resistance is the ratio of driving potential to the quantity which is flowing. About thermal resistance. So what is the driving potential in case of the heat flow? So the driving potential is the temperature difference, which is analogous to this delta E. And what is flowing is the heat, which is analogous
Sir, heat Q.
heat, which is equal analogous to the current. So that's why the thermal resistance is given by this expression. Now done this. So thermal resistance is the ratio of delta T by Q, right? So we have already derived this equation. So Qx is minus K dt by dx. I am writing it for the slab from the previous slide. So K by L, Ts1 minus Ts2. Now I will try to write this equation equivalent to this in the delta T by Q. Right? So the thermal resistance for the conduction, that too for this particular case, plain wall. Don't generalize this equation for any other case. For plain wall I am writing. So RT, T stands for thermal resistance, R for resistance, and this is conduction. Thermal resistance of conduction. In case of slab, you should write. This is given as Ts1 minus Ts2 divided by this is driving potential divided by the rate of heat transfer Qx, which is flowing through the system. So this will be equal to L by Ke. You have to just readjust the terms in this. So take this Qx on this side and this L by K on the other side. K by L on the other side. So this is how the RT conduction is defined for the slab. The thermal resistance of conduct due to conduction in case of slab is L by Ka. Note down this. Fine. Should I go ahead?
Yes, sir. Yes, sir. Sir, units. Sir.
So what will be the unit? You can find out from this. See, thermal resistance is given as L by Ka. Put the units of length, the thermal conductivity and the area, and tell me what should be the unit now? Follow. Is it like this? Check.
Yes, same.
Watt per meter K multiplied by meter square, right? So if you solve all that stuff, you will get Kelvin per watt or degree C per watt, right? Now, why these two units can be used interchangeably? Because here it is delta T and not absolute temperature. So both units are acceptable, huh? Kelvin per watt or degree C per watt. Fine. Now, so we defined what is the thermal resistance due to conduction. Now it is time to define thermal resistance due to convection. Now for that I have to invoke the Newton's law of cooling and expression. So I am writing Q is equal to HA delta T. We know this. This is based on Newton's law of cooling, right? So
yes,
Ts minus infinity is your driving potential delta T. Now I will write this expression in this fashion. So temperature difference Ts minus T infinity is driving potential divided by Q. So this term has to be taken on this side. So it will be 1 upon HA, right? So same thing I have written here. So RT, thermal resistance due to convection, is equal to driving potential Ts minus T infinity divided by the quantity which is flowing, the rate of heat transfer Q. And this is given as 1 upon HA. Clear?
Yes, sir.
So anytime if you want to find out the thermal resistance due to convection, you can use this equation 1 upon HA, and the unit will be similar to this as that. You will get the same. Fine. Thermal resistance due to convection. Now on similar lines, we'll also try to define thermal resistance due to radiation. And if you remember, maybe 2-3 lectures back, I made a statement that why we call this H as a convective heat transfer coefficient. Because you can define one more term called as a radiative heat transfer coefficient. I am going to use the symbol HR to represent that. So that's why this H is called as a convective heat transfer coefficient or convection heat transfer coefficient. Now the thermal resistance due to radiation. So we know this equation. Q is sigma epsilon Ts raised to 4 minus T surrounding raised to 4. This is based on Stefan-Boltzmann law and the derivation thereafter. We know this. Now Q radiation is defined writing the equation parallel to this. See, this is how the equation for convection is written. Q is HA delta T. So similarly, you can write Q radiation. This is convection heat transfer. Q radiation you will write. H will be replaced by HR, which is the radiative heat transfer coefficient. A will remain as it is. And the temperature difference is written as Ts minus T surrounding, because we have that temperature difference here, Ts minus T surrounding. Correct? Right? So if I want to rewrite this equation in this form, then I have to write the expression for HR here, that is the radiative heat transfer coefficient, equivalent to this. Then these two equations are one and the same. So HR, the radiative heat transfer coefficient, will be given as epsilon sigma Ts plus T surrounding in one bracket, and in second bracket Ts square plus T surrounding square. So if you put this value here, you will get the same expression. That's the idea. The only thing is why we are writing it like this, because we want to define what is the thermal resistance due to radiation using this kind of expression, delta T by Q. Correct? So now,
So sir,
right?
do we have to remember the value of HR that you have enclosed in box?
No, yes. Without this expression, you cannot simply do this, no? Right? You have to. You should know this expression. The radiative heat transfer coefficient HR is.
Sir, how it came, sir? I mean, how it came? I mean,
Hello.
yes, sir. I mean,
See,
hello.
you have to expand this bracket. See, this term, how you are getting this term? T square plus T surrounding square. So it is something like A square minus B square, no? So how you write A square minus B square? Right?
Yes, sir. Got that. So sir, you meant to say that A4 minus B raised to 4. That we have to simplify, no?
You have to split that.
Okay.
Right. Okay?
Okay.
You will get this. Nothing big in this. Now, on similar lines, you will define what is the thermal resistance due to radiation here. So RT radiation is again the driving potential, which is temperature difference Ts minus T surrounding, divided by the heat transfer due to radiation, Q radiation. So RT radiation will be given as 1 upon HRA. Same expression, 1 upon HA, 1 upon HRA, but the definition of H is different. So here it is convective heat transfer coefficient, here it is radiative heat transfer coefficient. So if you want to find out the thermal resistance due to radiation, you must know HR, and to find out HR, you must know this equation. That's why I said you must remember this. Is it clear now?
Yes, sir. It's clear.
Okay, fine. So we have defined the thermal resistance, which is basically the ratio of driving potential to the quantity which is flowing through your system. Here it is the heat transfer or the rate of heat transfer. So we defined thermal resistance for conduction, convection, and radiation. And we also remember that the RT conduction is equal to L by Ka. This expression is only applicable for plane wall and not anywhere else. So applicable for plane wall. However, you can use this expression all the time for this expression for any general case, and then solve it from this equation onward, and not like this. Clear? So here you will have the different expression in case of the cylinder, or the different expression in case of a sphere, and then you have to simplify it further and find out what is R conduction of a sphere, R conduction of a cylinder. We'll do that exercise also in coming slides. Fine. So timing, you just remember RT conduction, RT convection, and RT radiation, and the radiative heat transfer.
Sir, is there any restriction for RT convection and RT radiation, like as you told for conduction in case of plane wall only?
You're talking about values?
No, sir. the thing that you have enclosed in colored brackets of the thing, like here you told na, like RT convection is for plain wall only.
See, this is general. This is general expression. Now you change the geometry, area will change, right?
Yeah, sir, got it.
It will not. You change the geometry, accordingly the area will change. But this term invariably will remain 1 upon HA only all the time. Clear? Now take down the one more case. Now we are going to add some sort of complications here after. The plane wall with convection on both sides. Now this is your plane wall. So previously we had only these temperatures, right? And nothing we were talking about this side or this side. Now consider there is convection taking place on both sides of this slab. So on this side you have the hot fluid having temperature T infinity 1 and the heat transfer coefficient H1, and on the other side you have the cold fluid having temperature T infinity 2 and the heat transfer coefficient H2, right? So ideally if you know these two temperatures, then this is the temperature distribution which is very linear. But as there is convection happening from this side of the fluid to the surface, so that's why this line is there or this distribution is there. Same way, this temperature distribution is because of the heat transfer taking place from the surface to the surrounding fluid. Is it clear? And Qx is the rate of heat transfer along x direction. Fine? Is it clear?
Yes.
Okay, fine. Now here is the resistance circuit drawn similar to your DEE case. Basic electrical engineering, you know how to draw these series and parallel circuits, right? So there are three resistances in series. So the quantity which is flowing is the rate of heat transfer Qx, and it is flowing in this direction. Now the first thermal circuit is the convection resistance here on this side. So what is the temperature driving potential for that? Temperature difference between the temperature of the fluid and the surface temperature. So that's why T infinity 1, Ts1, and then this resistance in between is drawn. So draw this much first, fine, and then note down this temperature T infinity 1, then Ts1 at the nodes, and the resistance. Now what type of resistance it is? Convective type of resistance. So you can note down it as R convective, let us call it as 1. So R convective 1 is given as 1 upon H1A. Now see, H is on the side 1, so that's why H1A, right? Now, so you reached at this point now, correct? Now what is happening through the thickness of this slab is the conduction, right? And what is the driving potential for the conduction? It is Ts1 minus Ts2, the temperature difference, right? So I will take the second node and note down the temperature Ts2 and draw the resistance in between like this. So this must be the conduction resistance, right? And as this is slab, I am writing it as L by Ka. So this is R conduction or RT conduction, and this is for slab. Now here we know it is slab, that's why we are not writing L by Ka. Clear? And now last, you reached at this point. Now there is convection taking place from this surface to the fluid on this side. So I added one more resistance, and temperature or the driving potential is this Ts2 minus T infinity 2, and then I noted down what is the convective resistance on side 2. So convective resistance on side 2 is 1 upon H2A. It's very simple. Or now write on this. See, under steady state condition, the rate of heat transfer, this is constant. Qx is constant under steady state. Means if I take only this much temperature difference into account, and if I divide this by the convective resistance 1, which is this, then also Qx you can find out the rate of heat transfer, and this will remain same. So that's why if I take the second resistance and write Ts1 minus Ts2 driving potential divided by the resistance L by Ka, then also it is correct. Or if I take the last resistance into account and write down this temperature difference and divide by the resistance convective 2, then also it is correct. So Qx is constant or same.
Sir, one doubt, sir.
Which
Sir, So like in electrical circuits, we considered current to be constant in a series. So similarly, can we remember that heat transfer is constant if it is in series?
Not necessarily you can compare it as it is, but for the case which we are talking about right now, see, this will happen under steady state only. This is what I'm saying.
Okay, sir. Okay. It's, and sir, is there something any formula to add the resistances for getting
Similar electrical
equivalent
analogy.
or?
See, electrical
Oh,
analogy we use. How you do in electricity, the resistances in series, you add it, right? So that part is there.
yeah,
Also.
sir.
So in short, you can write this expression. Now, what is the basis for writing this? See, I am writing the driving potential as overall temperature difference, right? Numerator side. So what is the overall temperature difference in this? The highest temperature minus the lowest temperature. So T infinity 1 minus T infinity 2. So this is our overall temperature difference or the driving potential. Now if I divide this by all the resistances which are there right from this point to this, then also it is correct Qx. Get me or not? So that's why this is written as R total resistance or total thermal resistance. Is it clear?
Yes, sir.
So the total resistance will be given by this expression. So it is sum of the resistances. Now here these three resistances are in series. So our total resistance will be given as the convective resistance 1 plus thermal resistance of the slab plus the convective resistance 2 on this side. Convective 1 plus thermal plus convective will give you the total resistance R total. Clear?
Yes, sir. We are done.
Fine. So here we learned how to write down the expression for the total resistance and then find out the rate of heat transfer using that total resistance and overall temperature difference. So the idea is if you know the overall temperature difference without knowing these interface temperatures, somehow if you know the resistance offered by these individual components, using that total resistance you can find out what is the rate of heat transfer. That's the idea behind it. Now look at this composite wall. Now we have increased the complication further. Here we have the convection plus only one slab. Now here we have the convection on both sides plus there are three parts of this slab.
So composite wall, it means that there are three walls.
Three walls connected together, maybe you can say. So consider these as three walls, wall A, B and C connected together, having the thermal conductivity Ka, Kb and Kc. So these three are of different material and you can assume the different length also or thickness, La, Lb and Lc, different thicknesses for these three. And then the hot fluid on the left hand side and cold fluid on the right hand side. Not necessary, it should be like this only. You can reverse the direction also. The temperature, this profile will change accordingly. Fine. So the temperatures T infinity 1 is of this fluid and T infinity 4 is of the cold fluid. Then the surface temperature, call this as surface 1. So that's why TS1. Then T2 is the interface temperature. This temperature is called as interface temperature. T3 is the interface temperature because two faces are coming together, right? And this is the surface temperature at the outside, TS4. And T infinity 4 is the temperature of the cold fluid, right? So if you understood the previous case, then it is very simple. So the circuit is there, the thermal circuit is there. So the heat transfer is taking place in this direction. So Qx is shown, and then all the temperature differences or all temperatures are shown by the at these nodes 1, 2, 3, 4, 5, 6 nodes. So this is one node, 2, 3, 4, 5, and 6 nodes, and the resistances. So on this side you have the convective resistance. So call this as R convective 1. Then you have the thermal resistance of this slab. So this is R conduction 1. Conduction resistance of the slab 1 or part 1 of the slab. Then we have the second resistance, this one. So R conduction 2. Then the third one is R conduction 3 of part C. And at last we have one more convective resistance on this side. So this is R convective 2. I have used one here, that's why I'm writing here R convective 2. So the next step is simply find out the R total resistance, which is sum of these 5, and then use this expression. So we know, or rather I would say throughout the conduction part, everything can be written using this expression. Everything can be written like this. Remember this. So the rate of heat transfer is overall temperature difference divided by resistance. You can write the expression in this form all the time in conduction. So same thing we are doing here, Qx is. Now this is overall temperature difference, T infinity 1 minus T infinity 4, divided by sum of all the resistances which are between these two nodes. So these 5 resistances. Right? Is it clear? So
Yes.
now this is, I already explained this part in the previous slide itself, right? Then this time we'll introduce this concept of the overall heat transfer coefficient. So what we are trying to do is we are trying to write the expression in this form: Q is equal to HA delta T. This form, Q is equal to HA delta T. So if you want to write the expression in this form, how to represent this term? So that is shown here. So Qx is written as UA delta T, where this U is called as overall heat transfer coefficient. So here we will take into account all the resistances which are there offered by the composite cell. And if you compare this expression, with this, then you can write the definition of, or you can write the expression for the overall heat transfer coefficient in terms of total resistance. Write this expression now. So I am simply writing Q is equal to UA delta T. UA delta T. So this delta T will go out here. And then when you compare these two, QX, then UA will be equal to 1 upon summation RT, right? Or R total, right? And then you can write what is U, overall heat transfer coefficient. So it will be 1 upon R total into A. Getting me or not? Hello?
Yes, sir, getting it.
Fine. So write down this expression. The overall heat transfer coefficient U is given as 1 upon R total into A.
Yes, sir, we are done with it.
Okay, fine. So this is the final form. So R total is nothing but the summation of all the resistances here. So it will be written as overall driving potential divided by the rate of heat transfer Q, and then it is equal to 1 upon UA. So you can remember this expression: R total is 1 upon UA. Remember this. So if you are asked to find out the overall heat transfer coefficient U, you can find out using the total resistance. That's the idea behind it. Now this is true for the slab case only, where this area is constant. This area is constant here, right? So that's why this definition U is consistent with this. Now the definition of U will change if you change the geometry. For a cylinder or a sphere, this will be different expression, right? Whereas this will remain intact, that 1 upon R total into A, this will remain intact as it is. This will vary. Fine. Now can I go to next slide? So remember this equation: R total is 1 upon UA. Can I go to the next slide now? Or we are running out of time?
Yes, sir, we are running out of time. Sir, we have practicals also.
Okay. We will stop. Just give me a minute. Let me start the recording first.